This is HLAA vectors, day number 3 on the scalar product of vectors. Okay, so for vectors A and B, the algebraic scalar product is as follows. A dotted with B, or the scalar product of A and B. So just so you know, scalar product is also referred to as the dot product. Later on, we'll also talk about the vector product, which is the cross product, but that's not for today. So here is, by definition, the algebraic scalar product. Now, how does that come to be? If you have two vectors, A and B, let's say you have A1, A2, there's vector A, and you take the scalar product of that with B1, B2. What you do is you multiply the horizontal components A1 and B1, which gives you A1, B1, and you add it to the product of the vertical components A2 and B2, which is A2 times B2. Therefore, by definition, we get A1, B1 plus A2, B2. Okay, the geometric scalar product of vectors A and B is actually given by the following, and we're not proving this. This can be proven and actually will be proven in your homework assignment using the law of cosines. So these two expressions here are actually equivalent. Again, those will be proved by you in the homework. Okay, so what does this mean? This means that A dotted with B, or the scalar product of A and B, is also equal to the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between two vectors. So let's say I have vector A headed this direction, vector B headed that direction. Okay, the dot product or scalar product can also be determined using just what I know about A, B, and the angle in between. Okay, it will follow then, naturally, algebraically, if I took and divided both sides of this by the magnitudes of both A and B, I could then get myself to a point where I could solve for the angle between two vectors, which would be the inverse cosine of the scalar product of A and B over the magnitude of A times the magnitude of B. And that'll find us the angle between the two vectors. So let's get into a few examples. Okay, we'll start slow here. First example, find the scalar product of vectors A and B. Now I prefer to have my vectors in this column vector form like vector A is, so I'm going to convert B into the same form. So I have a column vector for vector B, which would be -1, -4. Now I can work with these two vectors and find their scalar product. So A dotted with B, or the scalar product of A and B, will be the vector 2, -1 times the vector -1, -4, which will equal 2 times a -1 plus -1 times a -4, which comes out to be a +2. So the scalar product of vectors A and B ends up being a constant. Now it's interesting. The result of a scalar product of two vectors is not a vector. Okay, it actually just ends up being a constant. It's very interesting. We'll see more with that in a minute here. Okay, example 2. Find the scalar product of the vectors A and B, given that we know a little bit of information. Okay, so we know that the scalar product of A and B is the magnitude of A times the magnitude of B times the cosine of the angle in between them. Okay, so I can find the scalar product using what I know, which is that the magnitude of A is 3, the magnitude of B is 5, and the angle between the two vectors is pi over 6. All right, so A dotted with B. Now these arrows, symbols above A and B are not necessary. That's just the form that I like to work with. As long as you're consistent, it doesn't matter. So I would have 15 times square root of 3 over 2. So our scalar product comes out to be 15 root 3 over 2. All right, outstanding. Let's look at a few more examples applying some of the geometric properties. Okay, next example says find the angle in radians between vectors A and B. Okay, so just imagine that vector A is placed on the Cartesian plane, right? So our xy plane. And imagine that I take this vector, which clearly is moving to the left and then up, and I place the tail of this vector at the origin. I'm allowed to do that if there is not kind of an initial position provided. And we go left, root 3, and up 1, and we get our vector A. All right, there it is. And our vector B, clearly we would be moving from the origin to the right 2 and down negative 2 root 3. So let's go to the right 2 and down. I should go down to here, negative 2 root 3. All right, so kind of like, that's not going to be very good. I'm going to move this over just a smidge here to make a little space. There we go. Okay, so there is vector B. So I got vector A, I got vector B, and we want to find the angle in radians between the two. Now, you might be kind of stumped as to decide whether we go with the angle less than 180 or greater than 180. And the answer to that is you always take the shortest angle from vector to vector. Okay, so you can ignore the blue angle and go with the green. Okay, so with that in mind, you know that your angle will always be less than or equal to 180. Okay, so how do we determine that angle measure? Well, we already know how to. To find any angle between two vectors, we take the inverse cosine of the scalar product of the two vectors over the magnitude of one times the magnitude of the other. Okay, so we just got to do a little bit of math. Let's first find the scalar product of the two. Okay, so that would be negative root 3, 1 times 2, negative 2 root 3, which would result in negative 4 root 3. Okay, so the scalar product of A and B is negative 4 root 3. Let's find the magnitude of A and then the magnitude of B, and we'll be ready to go on finding the angle. Okay, magnitude of A, let me go ahead and sketch a triangle here. Negative root 3, this would be a 1, that would make this a 2, right? This would be a 30-degree angle. Pi over 6, therefore, the magnitude of A is 2. Okay, the magnitude of B, let's go down here. Draw ourselves a right triangle. This would be a 2, this would be a negative 2 root 3. That would make this our 30-degree angle, and thus this angle would be 4. Excuse me, the magnitude would be 4. So the magnitude of B is 4, the magnitude of A is 2, and now I can find the angle measure. It's going to be the inverse cosine of the scalar product, which is negative 4 root 3, over the product of the magnitude of A and magnitude of B, which is 8. This is equivalent to the inverse cosine of negative root 3 over 2, which by my calculations, using what I know to be a unit circle friendly ratio, this one right here, would tell us that theta is 5 pi over 6. Okay, so the angle between the two vectors is 5 pi over 6. Let's examine, does theta, this angle right here, look like 5 pi over 6? Based on my sketch, it's pretty good. Okay, I can trust my math, and so I'm going to go with 5 pi over 6. Okay, let's look at another example here. In this next example, we're going to find the angle in radians between these two vectors, but now the vectors are three-dimensional. Okay, so we got to do the same process that we did in the last example. We got to find the scalar product of A and B. And I'm going to do it without really kind of laying it all out here in this example. I'm going to go 2 and a 3 and a negative 1, and I'm going to multiply the components together and add them together. Okay, so 2 times 1 is 2, plus 3 times 2 is 6, minus 1 times 4, which would be a negative 4. So it looks to me like I'm going to get a 4. So the scalar product, also known as the dot product, would be 4. Magnitude of A is going to be the square root of 2 squared plus 3 squared plus negative 1 squared, which comes out to be the square root of, oh gosh, is that 14? Like that. Magnitude of B. Very similarly, it's going to be the square root of 1 squared plus 2 squared plus 4 squared, which comes out to be the square root of 21. Okay, so the angle between the two vectors, theta, is the inverse cosine of the scalar product over the product of the magnitudes. I think I got those magnitudes right. 16, 4, and 1, that's 21. Very good. Okay, now comes your calculator. All right, so if you're in radian mode, which you should be, you should get 1.34 radians to 3 sig figs. If you're prompted for degrees, that would be 76.5 degrees. Okay, let's continue. Okay, so something interesting to note about the scalar product of two vectors is that if A and B, when we take our scalar product, equals 0, then one of three things is true. Either the angle between the two vectors is pi over 2, or one of the vectors is the 0 vector. Now, if one of the vectors is the 0 vector, this is really just not very interesting. Okay, so typically, if we get a scalar product of 0, the two vectors are what we call orthogonal. You can see that down here. Okay, so if the dot product of two vectors is 0, then the vectors are perpendicular. Likely, okay? Or one of these two goofy situations is taking place. If the dot product of two vectors is greater than 0, think about this now, that means, right, so if this value in the numerator is positive, right here, we already know that the magnitudes will be positive. So that makes the cosine, whoops, I screwed that up. Okay. That makes the cosine of theta greater than 0, right? So if A dotted with B is greater than 0, we already know that the magnitudes products will be greater than 0, and therefore the cosine of theta will be greater than 0, which means that the angle will be in quadrant 1. Therefore, if A dotted with B is greater than 0, then the vectors enclose an acute angle. Okay. The opposite for if A dotted with B is less than 0, then we get an obtuse angle between vectors. Now, angle between vectors, this is important. Okay, let's do this. Okay, here's the angle between the two vectors in this case. Okay, what if I have two vectors that look like this? Okay, what I have to do is translate one to the other, right? So I have to go tail to tail. So I could take this vector here, shift it down here, and then I get this angle right here. Okay, so don't be fooled into thinking that it's just the vertex at which the two vectors, based on their orientation, intersect. It's when their two tails, right, match up. And then we can find the angle in between. Of course, we take the smaller of the two angles. So it's not this angle. It's not this angle phi. It's the angle theta right here. Okay, let's look at a couple important properties and then we'll get on to some more work. I screwed something up there. There we go. Okay, just a couple things to note. A dotted with B, or the scalar product of A and B, is the same as the scalar product of B and A. the scalar product of A with itself is actually the magnitude of A squared. The scalar product of A with B plus C is the same as the scalar product of A with B plus the scalar product of A with C. Okay, and then a little bit of commutative property here. Lambda, which is just some constant, times the scalar product of A and B is equal to lambda times A, its scalar product of B, which is equal to A times the scalar product of A with lambda B. Okay, you'll probably see this show up in the homework. You'll need to show it just using component breakdown. Okay, let's look at a few more examples. All right, this is a very interesting problem. So let's go ahead and go through it. We're going to see the definition of both the scalar product and the magnitude show up. Okay, so the vectors A and B have the property given below. Find the angle between the vectors. So what we know is we know the magnitude of A, we know the magnitude of B, and we know that these two vectors, A plus B and A minus 2B, are perpendicular or orthogonal. Okay, so let's do a little work to kind of see where we go with this. Okay, so A plus B, what is that? Well, I can write that vector as A1 plus B1 and A2 plus B2, right? I just take the horizontal vertical components of each vector, add them together. Okay, how about A minus 2B? I don't know if yellow is going to show up very well for you, but I gotta go with it. That's A1 minus 2B1 and A2 minus 2B2. Okay, so if those two vectors are orthogonal, then that means that their scalar product is 0. So A1 plus B1, A2 plus B2, and the scalar product of that with A minus 2B, which would be A1 minus 2B1 and A2 minus 2B2. All right, we know that this is going to equal 0. All right, so we got to do a little work. Let's go ahead and get into this. First, I'll lay out what I'm about to do, and then I'll do some algebra. So I'm going to take A1 plus B1 times A1 minus 2B1. Okay, so hang with me here for a moment. If I do that, get A1 squared minus 2A1B1 plus A1B1 minus 2B1 squared plus, now I'm going to work the vertical component A2B2, or A2 plus B2, times A2 minus 2B2. Now the nice thing about this is going to look exactly like the first expression except with A2s and B2s instead of A1s and B1s. So this will be A2 squared minus 2A2B2 plus A2B2 minus 2B2 squared. The sum of those two is equal to 0. Now I'm going to actually compress this term right here, those two terms, they are like terms, and those two terms right there to give me A1 squared minus A1B1 minus 2B1 squared plus A2 squared minus A2B2 minus 2B2 squared. Okay, so where do you go from here? Well, I mentioned at the beginning that I was going to utilize the magnitude of A. So what is the magnitude of A? That's going to be A1 squared plus A2 squared. Right? So if I look at vector A, horizontal vertical component, this is A1, this is A2. So the magnitude of A, right, comes out to use the Pythagorean theorem and equals this. Very similarly, the magnitude of B will equal B1 squared plus B2 squared. Right, very similar sketch. Okay, so let's see if we can identify potentially some relationship between the magnitude of A and our expression here. Okay, so you may or may not see it, but I see an A1 squared here, and a2 squared there. So what I'm going to do is I'm going to pull those out here and go a1 squared plus a2 squared and group them. Okay, similarly, I'm going to take this b1 squared and this b2 squared. I'm going to factor out a -2, and I'm going to group those two together, b1 squared plus b2 squared. Okay, and then I'm going to take what I got left. Okay, I don't know what color I'll put it in. Maybe I'll just put it in black. Here we go. I got a1, b1, a2, b2. I'm going to factor out a -1 and put in a1, b1 plus a2, b2. Okay, now let's talk about this for a moment. How does this expression relate to the magnitude of A? Well, it's actually the magnitude of A squared, right? Because the magnitude of A is the square root of a1 squared plus a2 squared. So the magnitude of a squared takes care of the square root. Okay, cool. Then I have -2, and this will be the magnitude of b squared. And then this friendly little buddy right here, that's equivalent based on the definition to the scalar product of A and B. All right, so the scalar product of A and B is equal to, it's actually a value a1, b1 plus a2, b2. Okay, cool. So let's solve for a1, or excuse me, the scalar product of A and B. All right, so if I square the magnitude of A, right, if I square that, I get 9. If I square the magnitude of B, I get 4. So that'll be a 2 times a 4. And minus the scalar product of A and B should equal 0. That tells me that the scalar product of A and B should equal, looks like 1. Okay, so now I can find the angle between the two vectors. I've got enough information. I know that theta is equal to the inverse cosine of the scalar product of A and B over the magnitude times the magnitude. That should be magnitude. Good. So theta will be the inverse cosine. The scalar product of A and B is 1. The product of the two magnitudes is 6. And thus, if I am in radian mode, I get 1.40 radians. And in degrees, that is 80.4 degrees. All right, guys, there you have it. That is a very important problem that you should pay attention to, noting the difference between, well, all of the characteristics of the scalar product as well as the magnitude. All right, we got one more slide here. Let's get to it. Okay, so here we have our last example for these notes. I've got vectors A and B that are given with unknowns lambda and mu, which are real numbers. It says find the relationship between the real parameters given that A is perpendicular to B. Okay, so in part A, I know if A is perpendicular to B, then the scalar product of the two vectors 2 lambda and mu -5 should equal 0. Okay, so that tells me that 2 mu minus 5 lambda should equal 0. So there's our relationship, right, between those two parameters. Now, if you wanted to go further and say 2 mu is equal to 5 lambda, or mu is equal to 5 lambda over 2, you could definitely go that far. Okay, part B. Find the two possible vectors alluded to in part A, given that the magnitude of B is 13. So really all that I want to know is I want to know the two possible values for mu and the two possible values for lambda. And you'll see that kind of pop up here in the nature of this specific problem. So if I know that the magnitude of B is 13, well, the magnitude of B in terms of mu is the square root of mu squared plus 25, right? I just used Pythagorean theorem. Let's put vector B here out on the real plane. Actually, that would be poorly done. Let's say mu is positive for this example. know that vector b would look kind of like this, right? Here's my vector b, right movement mu units, downward movement 5 units, and we get Pythagorean theorem tells us that the magnitude of b was be the square root of mu squared plus 25. Okay, so knowing that, if I know the magnitude of b is 13, I can solve for mu. Okay, so I'm going to square both sides. That's a 169. That equals mu squared plus 25. Therefore, 144 equals mu squared. So mu equals either 12 or negative 12. Okay, so b, let's call this, I don't know, b alpha and b delta. Okay, so b alpha, let's say alpha comes first, so we'll go negative 12 for that. So b alpha is negative 12, negative 5. And b delta would be when mu is positive 12. Now there's no change with the negative 5. Let's match this up with a alpha and a delta. Okay, so a alpha would have a mu value, or excuse me, a lambda value that would match up with mu being negative 12. So if mu is negative 12, let's go over here. Mu equals negative 12. Then it looks like lambda will equal negative 24 fifths. Okay, which comes out to be 4.8. So how about a negative, oops, that should be a positive 2 and a negative 4.8. Okay, alpha, excuse me, a delta, this should be an a delta, would be, if mu were a positive 12, we would just get, of course, lambda equals positive 24 fifths, or 4.8. So we would get a 2 and a positive 4.8. Okay, so the two possible vectors alluded to in part A. All right, well, what are our two possible vectors? Well, we got them right here. All right, we've got alpha with negative 4.8 is mu, or excuse me, lambda. Alpha with positive 4.8, and then the two values for mu. All right, guys, that's it. We'll see you in the next video. Hope you have a great day.